This is a sequel of today's first episode. We are finalizing the innovator's dilemma, the conversation about the innovator's dilemma, and we're drawing conclusions for our portfolio. We discussed Tesla in the first episode. Now we're going to discuss the CRISPR index, synthetic biology, and the ideas around that part of our portfolio. This is the Not Even Wrong podcast. It's December 15th, 2020. Since the last update, the fund is up roughly 5%. So for the day, the fund is down about 4.8%, and the market's up 1%. We're up 368%. The market's up 13.5% for the year. We discussed Tesla at length, and we drew the conclusion that the Innovator's Dilemma, The Beginning of Infinity, The Innovation Stack, all these books are all building the principle stack that guides us very nicely towards Tesla. So Tesla fits the disruptive part of the innovator's dilemma very well. Tesla is a disruptive technology. Tesla is a fundamentally new concept with new engineering practices with large impact. We concluded that the three guiding vectors of Tesla that enable the company to still deterministically grow towards an uncertain future are convenience, price, and cash flow. So we concluded that after all the discussion of the innovator's dilemma, and particularly the identification of the fundamental problem of disruptive technologies, which is that they are new and therefore not researchable, that they create new markets, create new values, create new value chains. All these things are very difficult to foresee, and therefore the question comes up, well, how do you manage something like that? And the answer is you create vectors, you create north stars, and around which the technology can evolve. And in the case of Tesla, it's convenience, it's price, and cash flow. And now we want to have that same conversation about CRISPR. Now, let's be clear about CRISPR. CRISPR is a particular technology which allows the precise editing of the genome. This is what CRISPR is. We decided over a year ago that this is about as important of an invention as the transistor was in the last century. So what that means is that first and foremost, it's a fantastic invention. It's a genuine intellectual feast of creativity, of usefulness, all the good things that science can produce. But more importantly, also, it's building a new platform for a whole new technology stack that can be created around that technology. The same way the transistor was the beginning of a whole new technology stack that we call software and computing and Silicon Valley today. Now, within CRISPR, we have a couple of other interesting developments that are also part of our portfolio. First and foremost, synthetic biology, which is best replicated in our investment with Twist Bioscience. So synthetic biology is the synthetic development of DNA, RNA, of other molecules which are associated around DNA. So what you have is you have the natural DNA, which we can see in nature, but we can also replicate that. And Twist Bioscience has developed a way to do that fast at low cost. So you can order synthetic DNA from Twist Bioscience. You can also use that to do research. You can use that to store data. And you can also, and that's very encouraging, use that to increase the ability to read the genome. So there's a sort of a cross-fertilization there. The actual strength of synthetic biology is to have more insight into the natural biology, which gives us more insight into the synthetic biology. So there's this power law that we are very excited about, in particular for Twist Bioscience. So synthetic biology, which is not directly CRISPR, but of course there's a lot of CRISPR applications here. The next generation sequencing has direct applications to CRISPR, because you need to be able to read the genome, to edit it. And then we have another interesting investment that we have is base editing, beam which is in the base editing space. That's CRISPR 2.0. Without going too much into details, it's a more elegant, more precise way, less disruptive way to edit the genome. Certain applications which we believe can be also enhanced within the CRISPR space by using base editing, but more importantly, this is a technology which potentially could be even more powerful than CRISPR. It's the next generation of gene editing, and very interesting. We believe that building an innovation stack around base editing in itself also has a lot of potentiality, a lot of optionality. We have investment in Fate Therapeutics. Fate Therapeutics is a company that has pioneered the cell programming space, and what they do is, in particular, they take a skin or blood cell, they program it into a stem cell, and then reprogram that stem cell to become an NK cell or a T cell to attack cancer. So it's an immunotherapy company that attacks cancer by using cell programming. Not just CRISPR, they use CRISPR also, but they use other technologies to program the cells. So this is a little bit a further application, a more specific application. We would call this a vertical application of cell programming and gene editing. And then finally, we have also Pacific Bioscience, which is a company that is in the next generation sequencing, more precisely in the long read sequencing, which we believe is a disruptive technology in the sequencing space on its own. So having said all of that, I just wanted to give an overview over our portfolio that is not just CRISPR, but let's just start with gene editing and then try to draw the arc between gene editing and the conversation around the innovator's dilemma, around disruptive technologies, around new concepts and new engineering practices, and how that ties into our portfolio and into the wealth generation concept. So the ability to precisely edit the genome of humans, animals, plants, any kind of living being, is a very powerful method, because we believe, meaning we humans, the science, believes that the gene defines the RNA, defines the protein sequence, defines function. So we have a direct line between functionality in living organisms and the DNA. So if we can edit the DNA, we might be able to alter the functionality. This is the fundamental idea. The ability to do it precisely is nothing but, like it says, precision. Precision helps in many ways. In particular, it helps in actually getting something done. Of course, we're just at the beginning of this whole journey, so we don't even know exactly what kind of effects particular genes have. But in order to find that out, we have to be able to edit the genome, we have to be able to iterate, do research, and this is exactly what the CRISPR technology is allowing. Most importantly about CRISPR is that it is a very democratizing technology. So it's a technology that can be used in many labs, in many different contexts. So it's a low cost, you don't have to have a PhD to use it. All these things are looking to us like a fundamentally new concept with new engineering practices. And it has a large impact because it's low cost. So it's attacking a couple of vectors that we believe are important for a new invention, a new technology to start becoming disruptive in the Clayton Christensen way, which means it creates new markets. It allows for the development of new markets, new customer behavior, and the innovation stack can be built around that. Now let's talk a little bit more specifically about what kind of markets we could envision could be developed. And most importantly, let's start with the markets that already exist. There are a couple of therapeutic companies, public, CRISPR Therapeutics, Intellia, and Editas, the three that we own, Beam, which uses base editing, similar concept. What's happening there is that we think that certain diseases that have monogenetic causes, so one gene is the cause of the disease, We believe that if we can alter that gene, either erase it, edit it, fix it, that we can then solve the problem with the disease. And some of the diseases that are being attacked are sickle cell, beta thalassemia, some liver diseases, and some macular degeneration diseases. Those are diseases that we know are monogenetic. So one gene is the cause. We're not sure about the actual causes because we still don't know what the network effects within the genome are. So it could be that gene A is not just simply causing the disease, but gene A is maybe causing a certain network effect that then causes maybe the disease and so on and so forth. My point here is that we are thinking along the hopefully right lines, but there could be mistakes, and this is just the risk that we're running. So it's not that obvious that if gene A causes sickle cell and we fix gene A, then we don't have sickle cell. It's not that easy. We hope it is that easy and it's possible. So far, the results are phenomenal. Last week's ASH meeting showed positive results for CRISPR therapeutics in conjunction with Vertex. It also showed results that Editas published, Sangamo, which is a zinc finger technology similar to CRISPR, a bit more crude and less easy to use, but still, it seems like if we alter specific genes, we can actually attack specific diseases. Also, in the cancer immunotherapy space, the ability to program cells to attack tumors seems to work. Again, we are not sure about off-targets effect and other side effects. Of course, this is always a problem in therapeutic applications, but fundamentally, and this is now important for this conversation, so we have the ability to alter a gene and therefore fix a disease. That in itself is absolutely disruptive in a Clayton Christensen way because it allows for a one-shot solution to a chronic disease problem. This is amazing. This is huge. This is, of course, hopeful also for patients, but what it mostly does, it lowers costs dramatically for patients, healthcare systems, etc. We are also at the cusp of starting to build a new innovation stack around these technologies. In the past, it was much more of a try and error situation. We are bringing, and as Vijay Pandey from Andreessen Horowitz often says, we're bringing Silicon Valley practices into healthcare. We're bringing healthcare onto Moore's Law because once you start digitizing healthcare in a way that, okay, if you know certain binary events cause certain diseases, you can start using computational methods to start solving those problems, and CRISPR being the actual implementation of those methods. And once you're on the trajectory of Moore's Law, this is another massive potential effect that we believe is going to be very, very beneficial for the healthcare system as a whole, and also hopefully for the stocks that we own, because once they have the tailwind of Moore's Law, they will be in the same trajectory like Amazon or Tesla or Apple, where they can just benefit from Moore's Law and keep developing their innovation stack on top of Moore's Law, which is kind of like a power law in itself. Now, some of the things that we believe are different with the CRISPR technology than, for example, with Tesla or Amazon in terms of disruption is that we're talking here about a whole new platform technology. So this is not a company or an entrepreneur a la Jeff Bezos or Elon Musk, which is just simply changing the world or something like that. This is a whole new technology. So it's like I said several times, it is comparable to the invention of the transistor. And therefore, it has parallels, it has also uniquenesses, but the most important thing, I think, is that it increases a little bit our risk of not picking the right company, because CRISPR is a technology that is available to many people in many different contexts. And therefore, it's, of course, a question, well, are we at the right place at the right time? Or maybe we're too early, maybe we're too late. I don't think we're too late, but we could be too early and we could be investing in the wrong things because those markets are evolving. We don't see yet very clearly where those markets will be. But like I said before, one of the things we could potentially conclude is that a monogenetic disease can be solved with gene editing. This is possible. This is what we're betting on right now. In the future, there could be many more applications that we don't see yet and we don't want to conjecture necessarily. Particularly with Twist Bioscience, we did an episode a couple of weeks ago where we spoke about the disruptive effects of Twist Bioscience, and the two most important vectors there are, one is an iterative engineering style way of developing antibodies to attack diseases. This is one thing that Twist Bioscience is offering, and the other thing that Twist Bioscience is offering is storing data in DNA, which is completely new, unheard of. And we believe that there are markets that could develop in a Clayton-Christensen type way around that technology. So to summarize, we believe that our biotech index, which is formed around gene editing, synthetic biology, and cell programming, has a lot of aspects of fundamentally new concepts with new engineering practices. It has some aspects which are a little bit new, which make it a little bit more risky, because we might be betting on the wrong companies, because these are all platform technologies. They're not necessarily proprietary technologies to those particular companies. However, we believe that the companies that we're invested in are following definitely some of the vectors of our principal stack. They're building an innovation stack around a new concept, a new engineering practice. They're attacking new markets or existing markets with new concepts. For example, they're attacking diseases, sickle cell, beta thalassemia, by altering the genes and not doing other things that maybe have been done before. So these are new ways of attacking existing markets, therefore also hopefully creating new markets and new applications. There is new markets and new applications coming out of that. We are taking a bet here that the innovation stacks built around these new technologies will create massive new value, because it is lowering the cost and delivering solutions that in the past weren't even possible. Thank you.